Hey everyone, welcome to this explainer. Today, we're going to completely shift your perspective on the built environment. Just look around you right now. Your computer, your car, your desk, literally everything is made of separate individual pieces that are somehow connected. But how? Well, we're diving straight into the ingenious engineering that actually keeps our complex world from just falling apart. Picture this. You've got the ultimate manufacturing nightmare. How on earth do you assemble an incredibly fragile microchip onto a circuit board without completely melting it into a useless puddle? Seriously, every single day, manufacturers have to permanently attach these delicate, highly heat-sensitive components together, but without destroying them in the process. It's a massive challenge.
Section 1. The Heat Problem. Introduction to Non-Fusion Joining.
So let's dive into why traditional fusion welding, melting two pieces of metal until they become one, is absolutely not always the silver bullet. When we're dealing with intricate geometries, wildly mismatched materials, or those temperature-sensitive electronics we just talked about, blasting parts with extreme heat just isn't an option. Instead, engineers are forced to rely on this incredibly clever spectrum of non-fusion joining solutions that bypass the need to melt the base materials entirely. Over the next few minutes, we'll explore this whole spectrum, moving from liquid metals all the way to physical locks. Section 2. Liquid metals. Brazing and soldering explained. Let's start with high-heat liquid metal solutions. Unlike fusion welding, these techniques use heat just to melt a specific filler metal, which then fills the gaps between the solid parts, acting kind of like a metallic glue. And what's really wild is how a seemingly arbitrary temperature line completely separates two totally distinct industrial applications. That line is exactly 450 degrees Celsius. Above 450, we have brazing, which gives us incredibly strong structural joints. But drop below 450 degrees and you're soldering. Lower strength, sure, but it is the absolute, undisputed king of the electronics industry. Take a process like torch brazing. The copper tubes get heated up, right? But they don't melt. When the filler wire touches that hot joint, it melts. But here's the crazy part. Gravity isn't pulling it down. The molten brazed metal magically pulls itself into the microscopic interface between the parts. Through a phenomenon called capillary action, it literally sucks the liquid metal right up into the tightest gaps. Now, dropping back below that 450-degree mark, we enter the world of soldering. Every single one of those tiny silver beads on a printed circuit board is a vital solder joint holding a component in place. And, fun fact here, thanks to modern environmental standards, the industry has largely ditched toxic lead, shifting over to these really clever lead-free alloys like tin, silver, copper to make all these connections. So you might be wondering, how do they actually solder thousands of tiny components on a factory floor? Well, it's a fascinating, perfectly choreographed process. First, they apply a semi-solid solder paste. Next, high-speed machines place all the components down. Then the whole board goes into a furnace where the paste reflows and melts. And finally, this is the best part, the board literally surfs. It moves right over a standing wave of molten solder to coat the secondary side, and an air knife just blasts away the excess. Section 3. Chemical bonds, the power of adhesives and epoxies. Moving down our spectrum from liquid metals, let's look at the sheer versatility of chemical bonds. It's really easy to just think of adhesive as glorified glue, but industrial adhesives are absolute engineering marvels. They do way more than just hold things together. They actually seal out moisture and fluids to protect internals. They act as electrical insulators. They dampen vibration and noise, which is huge if you're building, say, airplanes or cars. And remarkably, they can seamlessly join completely dissimilar metals without causing any physical or chemical conflict. But hey, there's always a catch. The glaring weakness of chemical bonds is heat. While liquid metals laugh at high temperatures, chemical adhesives will generally just break down and fail when things get too hot. In fact, they're rarely suitable for service environments above 250 degrees Celsius. And they've got another major vulnerability: peel strength. Think about a piece of sticky tape stuck flat on a table. If you push it from the side, what engineers call shear force, it barely budges. Adhesives are incredibly strong in shear. But if you lift one corner and pull up, that's peeling. It comes off super easily. Adhesives are frankly terrible at resisting peel because the entire tearing force gets concentrated right at the leading edge. So how do engineers outsmart that exact weakness? They get creative. Take this case study involving a polycarbonate blood collection reservoir for surgeries. They needed a clear, light-curing adhesive. But the reservoir gets pressurized, which naturally creates those dreaded peeling forces at the joint. The solution? They physically redesigned the plastic parts with a tongue-and-groove configuration. This is brilliant because it protects the adhesive by forcing those peeling stresses to translate directly into shear forces instead. Section 4. Physical locks, mechanical fastening and assembly. Now let's pivot from permanent chemical bonds to physical solutions specifically designed to be undone. Why do we still use bolts, nuts, and screws? Simple. They are the absolute backbone of maintainable consumer products. They offer unparalleled ease of manufacturing and rapid assembly. But more than that, they make long-term maintenance possible. If a part breaks out in the field, you just unbolt it and swap it out. Plus, they allow for movable joints like hinges that static glues just can't handle. You've got to be careful though. Mechanical fastening comes with a really sharp warning about material compatibility. If you mix the wrong metals, say cranking a steel bolt through a copper sheet, you inadvertently create a tiny battery. This causes rapid galvanic crevice corrosion. One metal becomes the anode, the other the cathode, and the joint literally eats itself alive, destroying the structural strength in no time. Section 5. Tricky materials, joining plastics and ceramics. Let's see what happens when we're forced to step away from traditional metals entirely. Take thermoplastics. They have extremely low thermal conductivity. If you blast them with an external heat source, they don't melt uniformly at all. They just burn and char on the outside. So we have to melt them from the inside out. Engineers do this using high-frequency ultrasonic sound waves, or by literally vibrating the parts together to create internal friction, or even using radio waves. It's high-tech fusion, no flames required. And what about ceramics? They're super stiff, brittle, and incredibly heat resistant. If you try to braze a ceramic tip onto a metal drill bit, the metallic filler won't stick at all. So engineers devised this clever trick. They metallize the ceramic. By coating the ceramic with a slurry of molybdenum and manganese oxides and firing it, they basically give the ceramic a metallic skin. And once it has that skin, the brazing filler metal sticks to it perfectly. Problem solved. Section 6. The bottom line. Economics of joining operations. Finally, because engineering isn't just about what works in a lab, we have to look at what makes economic sense on a factory floor. When we look at the financial realities, the contrast in cost is stark. At the high end, you've got the expensive, labor-intensive precision of brazing, along with the recurring unit costs of individual bolts and threaded fasteners. But on the complete opposite end of the spectrum, with the lowest relative cost, you have seaming and crimping. Think of the top of your aluminum beverage can. That's a double lock seam. It's just folding thin metal at incredible speeds. No heat, no filler metal, and absolutely no extra parts. So what's the big takeaway from all of this? The next time you pick up your smartphone, sit in your car, or even just look at the desk in front of you, ask yourself, how is this actually holding together? Was it glued, bolted, brazed? The hidden engineering of our everyday environment is absolutely everywhere, once you know exactly how to look for it. Thanks for joining us for this explainer, and keep questioning the world around you.